Well, good afternoon, everyone. We start today's lesson. Today we discuss about the electromagnetic power that is transmitted with electromagnetic waves. Okay, and we also discuss the pointing theorem. Well, as we mentioned earlier, one of the most important characteristics of waves is their ability to transport energy and power associated with the process. And without this ability, most of the important applications of electromagnetics cannot be realized simply. Uh, and to examine the power and energy relations in the electromagnetic waves, it is convenient to look first at general time dependent expression for the rate of energy transfer, and we start with Maxwell's equation, as we do this always. So let's take the Ampere's law in Maxwell's equations, which states that a rotor of magnetic field intensity is equal to J plus the J plus the electric flux density varying with time, where term J includes all possible current densities, which is J is equal to J0 plus JE, or this is equal to J0 plus sigma multiplied by E, and where J0 indicates source current densities and JE indicates induced current densities in conducting media. Well, now we take this expression and we take this expression and we multiply this expression by E, both sides of this expression, where we will have E dot product of E with the rotor of H plus, or no, not plus, equal to dot product of E and J plus dot product of E and electric flux density variation with time. So from the Joule's law, we know that the P over the V is equal to E dot J, which is a watt per meter cube, which is the volumetric power density. It means that, okay, if we look to this expression, First term on the right hand side is volumetric power density, and the second term, we will discuss it further. Second term is also volume power density. Both terms on the right hand side of this equation, both terms of on the right hand side depend only on electric field intensity E. Therefore, and therefore, these are electric power density terms. Now, uh, we can integrate this term over the volume to calculate total electric power in the volume. Okay, before integrating, uh, do uh, let's do some manipulations with the left hand side of the equation. So we know the from vector identities that this expression is equal to h, or better h dot rotor of E minus E dot rotor of H. Okay, from where the E dot rotor of H is equal, well, simply H rotor of E minus the divergence of E cross H. Okay, this term is exactly the left hand side of our equation, and it means that these terms are the also can be thought as representing the power densities, and and from the Faraday's law, we can say that the H dot rotor of E is equal to the minus H dot dB over dV over dt. Okay. And as we mentioned earlier, all terms in this equation represent power densities, and all terms of these equations respectively are also the uh, power densities. But now these are these are the magnetic power densities rather than electric power densities. Mhm. And from from this equation, from the third equation, and from vector identities, we can write that the divergence of E cross H, so divergence of E cross H is equal to this term minus this term, and this term is equal to this, and this term is equal here to this expression. Okay, we were saying that divergence of E cross H will be equal to minus H dB dt. This comes from this page, so minus H dB dt minus, okay, here the second term is this, and this is in turn is equal to here to this expression, and E multiplied J plus the D over the T. E dot product of J plus the electric flux density varying with time, or is equal to minus H dB over the T minus E dot minus E dot J. Let's write first flux density just for convenience, minus E dot J, and this all we said the volumetric power density, watt per meter cube. So, assuming that we consider the power relations in a volume V bounded by an area of S, the total power in the volume is obtained by integrating over the volume. So, we integrate both both sides of our equation. Okay, we integrate this part with in V, and we integrate also this part in V. So we have E cross H dV over the volume V is equal to minus so H dB dt plus electric field intensity, electric flux density dt, so dV, and also minus the dot product of E and J d dV. And so left hand side of our equation can be uh, transformed into surface integral using divergence theorem. So left hand side will be equal to the integral over the S, integral over the closed surface S of E cross H ds. This comes from the divergence theorem. And also we use okay. So, and also we use the following identities, which are okay, E dot electric flux density with the derivative of electric flux density with time will be equal to d dt of E multiplied d over 2 and also H dB dt will be, it also goes inside the derivative, and we have H multiplied B over 2. Okay, with this and with these relations, our main equation will become uh, will will become so integral over the closed surface S of E cross H of ds will be equal to minus d dt integral over the volume H multiplied B over 2 plus electric field multiplied D over 2 over the volume V and minus the volume integral of E dot J dV. This is the power. Power and unit of measurement is watt. And so, if we perform scalar multiplications, H dot B is, okay, H dot B is mu, or not mu H, or mu multiplied H dot H. This will be equal to just mu by H squared without vector. Similarly, the electric field multiplied electric flux density D will be equal to E multiplied by epsilon epsilon multiplied by E, and this is equal to again epsilon multiplied to E squared. And our first equation will become the integral over the closed surface S of E cross H ds is equal to minus d dt so mu h squared over 2 mu h squared over 2 plus epsilon e squared over 2 dv minus v e dot j e dot j dv. Okay. So unit of measurement is watt. And the left hand side of this equation represents the total outward flow of power through the area S, bounding the volume V, or alternatively, the energy per unit time crossing the surface S. If this flow is inwards, uh, it is a negative flow. If outward, it is the positive flow. And expression the expression E cross H, or electric field intensity cross product with the magnetic field intensity, has the units of has the units of volt per meter cross the H has units of ampere per meter, which will become as watt per meter squared, and therefore it is the expression E cross H is a surface power density, and this power density E cross H called the Poynting vector, or okay, let me is equal to E cross H the unit of measurement we said watt per meter squared, and P called as Poynting vector. Okay. Well, Poynting is a last name of a scientist who was John Henry Poynting. Uh, and his his work was published in 1884, and the name of his works are now known as Poynting theorem and Poynting vectors. Okay, P is Poynting vector. Well, the advantage of this expression is that it also indicates the direction of the power flow. Information, the direction of power flow is important for wave propagation calculations. Well, and from this expression we may see that power flows in the direction perpendicular to both E and H, of course according to the right hand rule, which we used for vector product. which you already know. Well, this will be used often to define or identify the direction of propagation of a wave. Uh, we already know if electric field intensity E is known, we from proper Maxwell equations can find the magnetic field intensity as well. After that, we can define or find the direction of propagation of wave that we are examining. So if we go back to this expression, to this equation, the first term on the right hand side represents the time rate of decrease in the potential or stored energy in the system. And as we can see, it has two components. One is the time rate of change of the stored electric energy, and the other one is the time rate change of the stored magnetic energy. And the second term, which is this, is due to any sources that may exist in the volume. There are two possibilities that must be considered here. One is that the current density is a source current density such as produced by a battery or generator inside the volume V. And the second is a current density provided by external sources. Well, to understand this, let's see to the figure, to a scheme, of battery connected to a scheme of uh, electric resistor connected to the battery, or this is plus and minus, and this is the resistor. V, the flow of current, electric field intensity E, and also electric field intensity E, sigma. Okay, or better, we may draw it separately. Okay. This part can be thought as transmitter, and this part can be thought as receiver. Or if we look at this scheme, we may note that the current densities in the resistor and in the battery are in the same direction, and when we introduce the term EJ, when we introduce the term E dot J in pointing theorem, which was here, yes, here, and this will be this term will be positive if we introduce the source, and this term will be negative if we introduce the load. Okay. So, okay, and we said that E dot J may be positive or negative according to what we introduce. It will be negative if we introduce the load, and this term will be positive if we introduce the source. Therefore, we distinguish between two solutions. So, between two solutions. First, no sources in the volume V. No sources in the volume V. In this case, all sources are external to the volume. However, there may be induced current densities inside the volume. All power in the volume must come from outside sources. Okay, and also in any conducting material, the term J can be written as sigma multiplied by E, because all power comes from outside the volume. This case also called the receiver case. Here, the receiver case, and now pointing theorem will become, so the pointing theorem will become the integral over the closed surface S of E cross H will be equal to minus d dt. So V mu H squared over 2 plus epsilon E squared over 2 dV minus, okay, minus sigma E squared dV of V. So we may note that the both terms in the right hand side, this is the first term, this is the second term, are they are both negative. Thus the pointing vector P, which is E cross H, must be also negative. This means that power flows into the volume V. This must be negative, and it means that power flows into the volume, into the volume V. Okay, the second solution is when we think of second solution, there are sources in the volume. So sources in the volume V. Sorry, this is the second solution. So this situation is discussed in the following figure. Let me copy. This situation is discussed in the following figures. A source is located in the volume, but there are no losses in the same volume. Since the electric field intensity E and current density J are in opposite directions in the source, the product E multiplied J is negative. That's why the pointing theorem now becomes integral over the S E cross H of ds so is equal to minus d dt of integral over the volume V mu h squared over 2 plus epsilon e squared over 2 dv and plus the integral of e j as we expected, the flow of power is out of the volume. This is also called the transmitter case. And the transmitter case, and this case is shown can be seen in this figure. The first shows a transmitting antenna, such as from a mobile phone, for example. The power is transmitted out, and the second shows the microwave oven, and volume corresponding to our case is this is enclosed by magnetron, and this in our case is a source, and which is inside of volume V.